Hi there, my name is Alan Hong. I'm from Thoracic Technologies. I'm a Strategic Marketing Manager. And today, we're going to be introducing the I2C Write and giving a brief tutorial on how you can get started with your design. Now, let's first make the following assumptions before we begin. You already know the basics of Verilog, and you have worked with FPGAs before, and you know how to use Quartus 2, and you know how to use Signal Tap 2. With these out of the way, we can go ahead and right now, here is our platform that we're going to work with, our D0 Nano. Okay, so let's start by introducing what is I2C. I2C stands for Inter-Integrated Circuit, and it's a communication standard developed by Philips back in the 1980s for connecting ICs on the same circuit board. It's a two-wire interface, so there's an advantage that it doesn't require too many pins, and it operates on slower clock speeds compared to other communication protocols like SPI. Now, I2C is a communication between master and slave. And for this exercise, our master is going to be our Altera Cyclone 4 FPGA on our D0 Nano, and our slave will be a memory device. And as you can see on the top over here, we have our I2C clock, which is only one direction where the master is dictating it to the slave. And the I2C bus is a bidirectional bus. But for this exercise, we're only going to be writing to the memory device. So next, here is our I2C write protocol. And over here we have our start bit, where we'll get into detail later. We specify our control byte, and then an acknowledge comes from the slave. We specify the word address or register address, and another acknowledge comes from the slave. And then we specify our data to be written into the slave. And when that is done, then we can also get an acknowledge from the slave, and then we can stop the communication. Now, what do I mean by start and stop? If you look to the bottom over here, we have our start condition, which is basically when the SCL, or clock, is still high, the SDA, or data line, goes low, and the clock then goes low. Then we can start our data and address communication. That's known as the start condition. The end condition or stop condition is also very similar, where the SCL or clock signal goes high and the SDA goes high as well. So our slave device for today is an EEPROM that's located on our DE0 Nano. We're going to be using an EEPROM from Microchip, a 2 kilobit serial EEPROM, which stands for Electrically Erasable Programmable Read-Only Memory. These EEPROMs are non-volatile memories that are usually used to store small amounts of configuration information when the power shuts down. And our specific address today will be A0. I2C addresses are usually assigned to them by the manufacturer, and each I2C chip should have their own unique I2C address. So it's important to consider when you have multiple slaves assigned to one master on the same bus. Each of those slaves should have their own unique I2C addresses. So our operation for today is going to be writing a value of AA or 101010 into our memory address or register address of 00. Now to recap, our slave address for Microchip EEPROM is A0. That's going to go into our control byte. Our word address or register address of 00 is going to go into our word address, and our data, AA, is going to go into the data over here. And every time we specify our addresses or data, we should get an acknowledge from the slave. And the acknowledge is in the form of a low signal. So the slave itself will pull the data line low, to let us know that it acknowledges the address or data that the master is specifying. So before we start coding our DE0 nano I2C communication, let's open up our control panel. And I've already connected our FPGA dev kit onto our PC. So it's automatically detected and connected. And if we go down to memory, we can specify our memory type to our EEPROM to control our EEPROM. Over here we have random access. So at address 0, we can write whatever data we want and read from it as well. So first we'll start off by writing FF. If we read from the same address, we'll get FF as well. If we write 11, for instance, we'll also get 11. But we'll keep it at 0 for now. So now that's done, we can disconnect our control panel, go to our I2C test, which is a project I've already saved, open the Quartus project up. So now that Quartus is open, we can look at our top module, and we have our basic pin declarations. One thing to notice is our I2C S-clock pins and our I2C SDAT pins. And we've also, for the sake of testing, we've declared other pins, our count and SD counter. And I'll explain this further on. Now, I've included everything in our top module, which is a very bad exercise idea. In an ideal situation, you would include your I2C write module into another module, submodule. But for learning purposes, we'll keep everything on our top module for now. So clock, LED, key, switch, EEPROM, our SD counter, and count. Now, our regwire declarations. We have our reset, and it's active low, so we have N here. And this basically resets all of our systems for the I2C communication. We have our go signal, which is a flag to start our I2C write operation. Our SD counter, which is a counter to keep track of our I2C. And we have our SDI, which is a register value for SDAT, which stands for slave device input. And we have our S-clock, which is another register we're going to feed into our pin on the DE0 nano, a register value for S-clock, and our count. Now the count itself is going to be our clock. Our EEPROM operates on a maximum frequency of 400 kilohertz. So we're going to have to slow down our clock considerably, given that it's 50 megahertz. So we'll move on to our structural coding. Over here we can see that we've assigned our reset N to our key 0, and our always clock 50. Every time we have a positive edge clock 50, we'll count up our 10-bit register of count. And we can see that since it's a 10-bit register, we can assign the 10th bit of the register as our clock for the entire system, effectively creating a very slow clock, slow enough for our I2C protocol. So our always blocks from now on will start with pause edge count 9. So over here we can see that every time we reset, our go will equal to 0. If we press our key 1, then our go will equal to 1, which starts our I2C communication. So over here we can also see that we've set an I2C counter, and what it does is it forms a sort of a lookup table for us to base on what to do during our I2C operation. We'll get into that later. So basically we have, it starts at 0 if we reset it. If we don't press go, it's 0. If we press go, which is key 1, the SD counter will start counting up until it reaches 33, which is the end of our I2C operation. And this is very important because this pertains to our sort of a lookup table that we have down here based on our I2C counter. So getting into it, we have our case, which is based on our SD counter. Now, their default condition is that SDI and SCL are both high. And these correspond to our SDAT pin on our EEPROM and our S clock pin on our EEPROM as well. So they're both high in the beginning when SD counter is equal to 0. Now once it starts counting up, however, our SDI is the first one to go down. So that means that is our start condition over here, and SCL can go down as well. And then we can input a regular clock into our EEPROM S clock, and our SDI, given on the different counter conditions, we'll have different conditions. So first is our slave address. And first we'll input our A0, which is 10100000. And then after that, in order to get an acknowledge from the slave, we'll set our bus to tri-state. So the master will basically let go of the bus line for the slave to give an acknowledge. And if the slave pulls the line low, then we know that the slave has acknowledged. If there is no pulling low and what we get is a high signal, then we know that we haven't effectively communicated with our slave device. So after there's an acknowledge there, we can move on to our sub address, which is our register address, and we'll specify as 00000000. Again, we'll wait for the slave to acknowledge by setting our bus to tri-state. After the slave acknowledges, we'll write our data into our register 0. So it'll be AA, which is 10101010, and we'll wait for our slave to acknowledge. So that is the end of our operation. And what we have to do is we have to specify a stop condition. And the stop condition, while the clock is high, the SDI will go high. So over here, our SDI is still 0. Our S clock already goes to 1. And then our SDI goes to 1, specifying our stop condition, and our I2C protocol is ended. So our SDI register will go feed into our pin on the EEPROM, which is the I2C SDAT. We've assigned it here. And our SCL clock over here will feed into our EEPROM pin, given the condition that the SD counter is greater or equal to 4 or less than or equal to 31. So let's see this in action in Signal Tab 2. Going in now, we'll go to our setup, and we can see that we sample 4 different signals, which is our SD counter, our I2C SDAT, S clock, both from EEPROM, and our go signal. And our go is going to be our trigger, which we trigger at the rising edge. And the go will rise whenever we press our key 1. Our sampling clock is twice the speed of our regular clock, so it's the 9th bit of count, and our sample depth 1K. And since everything's connected, we'll go ahead and press program. And now it's ready to acquire. We'll acquire, wait for a trigger, and the go will go when we press key 1. So now we can see that we have our I2C signal. We have our go, which rises, which signals the start of our I2C. It starts our SD counter. And our I2C S clock will start as well. And over here we can see our start condition, which is when S clock is high, SDAT will go low. And our first call address will go to our slave address, which is A0. So we have 10100000. And since this bit is low, it means that the slave acknowledges our signal. Next, we have to specify a register address. So our register address is 0, so it's 000000000. And over here, the acknowledge, the signal is also low, so the slave acknowledges. And then we write a value of AA into our register, which is 10100000. 101010, and the slave acknowledges. And subsequently, we have our end signal, which is when S clock goes high, the SDA clock also goes high when the S clock is high. So that is our end signal. So going back to our control panel, we'll connect back again. And now that we're connected, we can go to memory, EEPROM, and like always, we specify the address to be 0. And if we click on read over here, then we should be able to get a value of AA, which is what we see right here. Now, in order to more deeply illustrate our slave acknowledge, we could specify a different address which doesn't match our EEPROM address. So if I were to change our slave address over here to say 111.00000, then we should not get an acknowledge from our slave. So we'll just compile this design. So now that the compilation is complete, we'll go over here and we'll download this again. And what we should see on this new run is that we should not get an acknowledge. And we'll do this again. We'll press down on our key 1. And as you can see, by specifying a different address, we don't get an acknowledge from the slave device. Over here as well. Over here. These are our acknowledge bits, and our slave does not acknowledge. So thank you for watching the I2C Write tutorial today. I hope it helped you in your design and getting started with your I2C communication. And as always, if you have any questions, please contact our support team at support@terasic.com. Thank you.